the rate of omega t, right? Radians per second times seconds equals, it'll go back and forth at a rate that is the square root of that constant. So it's like playing Monday quarterback. Retro engineering, we're reverse engineering. We're calling that constant omega squared.
Hello. 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 Bear with me for a minute. I'm coming in a funny order today. Hello. Welcome back from a long.
Good afternoon.
Thank you. Good afternoon. Thank you for saying that. I believe, was that Allison? Or Valentine? Good afternoon, Valentine. Was that Allison? Well, I'll look in the. Was that Allison? Can I ask? Who?
Yes, it was.
Oh, great. Thank you. That's voice right there. Good afternoon to you, Allison, and good afternoon. I believe Valentina just said good afternoon. We'll chat in a second. I know feel like it's been forever since I've seen you guys because it happened.
Good afternoon.
Good afternoon. That was Christopher or Chris. Good afternoon. Hold on. Let me get the board is coming. I know there's a lot of people in the chat. Hold on. I know it's been a long time. Hang on. Oh, and Tuwiba, thank you. Okay, hold on. Okay. Let me get rid of. Okay. Yes. Good afternoon. Good afternoon. Where's Mario? Okay. Good. Good afternoon. Okay. Sorry, almost there. Oh yes, and here's. Okay. Yes. Good afternoon, Dante. Good afternoon, Key. Good afternoon, Juliana. Good afternoon, Samantha. Hi, Michaela. Good afternoon, Bradley. Good afternoon, Bree. Good afternoon, James. Hi, and good afternoon, Samantha. Good afternoon, Tuwiba. Hello, Dennis. Good afternoon, Mario. Okay, we are here. All right. Okay. Let me. It's been a long time. It's been a long time. And we have to get. But you guys really rocked last Wednesday. Sort of beyond expectations. I think you're really on top of the Doppler effect. So we're going to just keep moving today. Hold on, let me put something in the chat here. Okay. I'm just putting this in the chat. We're going to be interrupted as usual. So I don't have your exams yet. I apologize. I have no excuse for that. I have nothing, and it's not personal. It's my slowness in the background. They're definitely not forgotten. I know you need the material and the grades, and they will be coming. And if that causes any personal crisis or like severe anxiety on your end, definitely reach out to me personally, and we'll try to talk about it. But I'll get them back shortly, as soon as I can. Oh, sorry. Okay. And also let me just turn off. There's all these interruptions. Let me turn off the interruptions. Whatever. But so I do apologize. I just want to be clear that I don't have them yet. The minute I have them, I will give them to you, and they may come one at a time to you. Some of you might get them back before others, but it's nothing about it has anything to do with anybody doing personally badly or well or anything. It's just taking me a while. I'm turning off interruptions, which as I can possibly. Okay. But I will say, I mean, I'm optimistic about this class, and we'll talk more. I know the class goes very quickly. If I think anybody's in crisis or if there's any real issues with anybody, I'll be talking with you personally, or you'll be reaching out to me personally. I know we have 2 more weeks. We will be together for much of these 2 weeks. There's one other thing. I will say though that oh, hi, hello, great to thank you. Yes, great to see you. Oh, no worries. I really think you're more on top of that Doppler effect thing than classes have been in the past. Maybe it's because your timing was so good, coordinate. You just happened to be doing it in lab and lecture at the same, whatever it was. I think you're on top of it. We'll revisit it. It will be on the final. But I think because you did so well with it, you seem to understand we are in a position, luckily, to press on for the last 40% of this class, which is about ultimately electricity and magnetism, as I think you've already begun in the lab. I believe you've begun circuits in the lab already. Actually, you should maybe confirm or deny that in the chat if you can. And if
Confirmed.
great, thank you, and oh, that's a lot of you. Great today. Oh, great. Okay, great. So somehow things you seem to be coordinating things very well, or they're coordinated for you. So I'm going to start giving you my take on electricity right now. In the lecture, there is a the homework that's in theory due tomorrow is about everything I'm about to say today. And then if you need more time to help you with more of it tomorrow, then we can, that can be a thing as well. But here we go. Oh,
wait, what's due tomorrow?
Okay, what? So did you say? Oh, sorry. There's something in the chat also. Did you just ask what's due tomorrow? Is that what you asked? In theory. Okay,
Yeah.
I think it just got posted, and you know what? In fact, since it just got posted, actually, I'm going to change it right now. What's in theory? I'm not going to change it, but I'll extend the deadline right now. What just got posted, in theory, for 4:05 p.m. tomorrow is a sheet called. Hold on. I'm getting to it. Called Homework 6 from G to E fields. In theory, it's due tomorrow. Right now, I'm going to change it and make it due the next day at 4:05. I might tuck something in also as well, but probably not. And of course, even if you re-update or re-upload things later, that's also fine. But yeah, all right. So I just changed the date. It's called Homework 6 from G to E fields. It's what we're going to start talking about right now. Like I am going to be this is kind of like what we did with, I don't remember, homework 2 or 3. I'm going to start walking you through the concepts that you need in order to do this homework, like right now. But it is a way of getting us to see how the electrostatic force ultimately yields the electrostatic field, and therefore all these things that you're doing in lab, including electric current. All right, but let me so I just changed the deadline to Wednesday, but can you see, and I'm going to open the sheet on the screen at some point in today's class, but do you see that on your side in Google? Am I right that there's a homework 6 from G to E fields? I'm in 3 screens at once. Yes, you see it. Okay, great. Oh, and someone's in the waiting room. Okay. Yes, you see it. Great. Thank you, guys. Thank you. Okay, and I don't know why that just happened. Mrs. Google, you don't need to help. Thank you. Okay. Okay, great. All right, so I don't know why because I just posted, I just changed it. Anyway, you see that. So the topic here, starting right now is electrostatic forces and fields. Oh, for anybody who just joined, I'm going to repeat something that was in the chat just for anybody who just joined. Hold on. No, wait, Sade put something in the chat. 1 second. Oh, thank you, Sade. Nope, that is my mistake. Okay, and you should really submit that for points. If I should make a portal for correcting the professor. Maybe I never did, but I'm sure you can find a portal to submit that for points. Thank you for pointing out. Yes, the game turn that's due tonight was not meant to be another game turn 9. Thank you. It was meant to be game turn 6, game turn 10. Also, this is all these like new numbering systems are partly just to help us always know where we are in the class. So thank you. Yes, I'm changing that right now. Thank you. Okay. And all those kind of things, hopefully you're seeing on your end, since I know we haven't seen each other since Wednesday, and last week was kind of choppy. As I am reposting in the chat, hold on. All right. Well, I'm just going to say again, I don't have your exams yet. That is my bad. I apologize. I'll get them to you as quickly as I mean, I'll get them to you as soon as I can. But most of the other stuff, I think a lot of stuff a lot of the points that I owe you or that you've earned, I think you've seen accumulated on your side, and they all do matter and they all do add up. So almost any work you've done at this moment, besides the exams, has gotten some amount of credit. In some cases, I still might owe you more credit for some of it, and you can reach out to me and let me know if that's the case, or if you did another draft, or I overlooked something, blah, blah, blah. But so again, if you're sitting and you notice the room is getting thinner and thinner each day, right? If you're still sitting with me and you're still standing by the end of the semester and you're still hearing all these announcements and all this material, that's a pretty good sign that you're still in the game and that you're the person I'm talking to when I say, I think you're doing fine. If I think there's a real crisis with you, either I'm going to be reaching out to you, or you know it and you should be reaching out to me. But if you're hearing me right now, I guess what I'm really saying is if your biggest concern right now is your exam grade, then I'm totally with you. That would be my biggest concern too, as a student. But the reason you don't have it yet is not a reflection that you didn't do well or anything like that. I think, and all your numbers are indicating, all your other numbers hopefully should be indicating to you that you are very much still in the game. Okay, I'm being interrupted. We're about to be interrupted by family who's coming home. I'm going to start on electricity right now. The front, but obviously interrupt me with questions at any time in the chat. The front sheet that you're looking at, I mean, the page of notes, has two equations on it. Okay. The first equation, you may maybe hopefully recognize some version of it from physics 2.
It reminds me, sorry, it reminds me of universal gravity.
Oh, perfect. I'm glad it reminds you of it, because that is exactly what it is. And thank you, Samantha, as well. Yes, good. And people may have seen it written in different ways at different times, but yes, Christopher is absolutely right. And Samantha is absolutely right that first equation, which we're going to start talking about. Oh, hold on one second. Did I mention we were going to be interrupted? Hold on one second. Hello, welcome. Was it good? Was it good? I'm teaching, but was it good?
Yeah, it was long.
Well, then, okay. Welcome back. It's great to see you. I can't wait to see you after I teach. Okay.
He's giving false information.
That's funny, actually. Okay. But it's great to see you. I want to hear all about it.
For the rest of the year.
No,
Stand here.
No. Okay,
Right
that's
here.
very clever. Oh my God. Okay. All right. Yes. Yes. Oh, I'm sorry to hear. How did you get hurt drumming? Oh, I guess it is more athletic. Oh, you do go outside? Oh, I'm glad they actually go outside. All right. I'm sorry to hear it. Bye. Good to see you. Okay. By the way, if you're still deciding whether to be parents, any of you in the room, if there's still time to decide whether to be parents, let's have a private Zoom conference and talk about that. Okay. Okay. I agree that it was good. Wait, I'm looking back. I'm looking in the chat. No, I love him like a son, really. And by the way, he apparently read his Galileo because he really believes not the Earth, but the sun is the center of the universe. Okay. Oh, wait, I agree that it was good, that universal gravity. Okay. Well, I'm not sure what Dennis. Oh, okay. I got you. Okay. All right. So yes, the first equation is universal gravitation. Right. That's yes. Thank you, Dennis. Exactly. You got it. Yes, that is whatever book Dennis is reading is definitely the book that my son is reading. Right. Yes. And I apologize for that. Okay. It shows he's so disappointed. Okay. But I'll take any of you down in a Pokemon battle of TCG. I assure you that. Okay. Or at least I'll take me down. Okay. The first equation. I'm going to start writing. The first equation is universal gravitation. In theory, this is a review of something you've seen before in Physics 203, but there's and we're going to review it quickly, though. If you haven't seen it, you're going to see it right now. But there's a reason we're revisiting it briefly in order to make a big compare and contrast with electrostatics. So in brief, here is the idea of universal gravitation. Right. And if you take this as a reminder of something you already know, fantastic. See anywhere that. Oh, yes. I'm sorry. Go.
Right.
Yeah.
I I know you see it's gonna be brief, but try not to make it too brief, because to be honest, this was the last topic we did, and we tried to sum it up in one class. So it was kind of learn it just to do the finals kind of thing. So I don't know if I speak for most of those who had Professor, I don't remember her name.
Walter.
Yeah, Professor Walter. Yeah. But that's one of that. I think that's the least grasped topic, at least for me. I don't know if I speak for everyone else.
Okay, no, that's very helpful for you to say. I really appreciate. As a matter of fact, you just remind. No, and if anybody thinks that he is not speaking, that Christopher is not speaking for them, oh, I agree. Okay, no, and you're welcome to put in a private chat. Look, I'm actually appreciate that he just did that. I'm going to take it very seriously, especially since now 3 of you are like whatever that word is for agreeing. Okay, no, and yes. I mean, yeah, okay. So I will slow down. Good. And you got to know, I mean, if someone's telling me talk a little bit more, not a little bit less, that definitely says something, right? Because I mean, I think that mostly people would rather me. I will take that seriously. If anybody in the private chat wants to say, no, I can't stand this, I totally get it. You could tell me in the private chat and I'll incorporate that too. But yes, okay, fair enough. I appreciate your honesty. And matter of fact, I was just with the Walterses last Thursday night, as a matter of fact. And in fact, Professor Walters, the one that you had, did also say something to the. I repeated to her what you all told me about the coordinate systems and everything, and I was so happy about that. And then she said to me, she's like, just so you know, I totally made, if they tell you that we never did the gravitation equation, we totally did. She's like, but basically we did it just enough so that they could never say that they never saw it. Okay. So yeah, all right. So fair enough. Oh, I'm going to talk to, right. Okay. So here's the deal with it. Here's the deal. But you feel free in the chat to tell me to slow up or slow down while I'm going. That's very helpful. I do want you to know it. So, okay, here's the idea. If you have okay. Okay, here's the story. Here's the setup. First of all, let's say we have 2 arbitrary point masses known as M1 and M2. Now, let me pause on, and they're separated by a displacement called R vector, a displacement vector called R. Now, okay. Oh, cool. Right. Cool. And thank you, Evelyn. I see what Evelyn's saying. And I also, quick sidebar for anybody like Evelyn or anybody who's coming from another school or whatever, whatever level of understanding you are coming in with about this gravity, I am going to quickly review it now so we're all thinking of it in the similar terms in this class. But I also want to say that part of what I'm going to try to use, I'm doing gravity for all of you somewhat briefly to set a context for us to compare electrostatics to it. Okay, so the ultimate goal here is to think about what goes on between electrical charges by comparing that situation to what goes on between masses. But let's just say you happen to be very, very comfortable with the physical background of this, or you're coming from another school, or you just heard it all in a different way. Part of what I'm also going to be trying to get across here to everyone, is certain kind of vector notation that we use when we're discussing these kinds of forces. So there's a little bit of math going on here too, a mathematical notation that I want to put us all on the same page. And it's the same mathematical notation that's going to apply to gravity as well as to electrostatics. So whoever you are, wherever you're coming from, another school or John Jay or whatnot, or Hema Walters was too fast for you, like you partly think about whatever physical things I try to say, but also try to think about, okay, he's making a point about how to use mathematical notation from here on in. And whichever you need to focus on more, focus on that. So here we go. In gravity, the premise, the idea is if you have any 2 points of mass, okay, so this goes back now to the beginning of the semester, like like you have 2 super tiny thingy things, 2 dots of particular massive discrete matter, right? 2 points of matter. So 2 clumps of matter that are each so small that they're in effect taking up an infinitesimal volume. They're like in the limit that, if they're a ball, they're like in the limit as the radius approaches 0, right? Each of them, but they're 2 arbitrary masses. So these 2 objects that you're picturing in your mind are 2 dots, but they're 2 dots of, if you like, 2 different densities. So one might be 1 kilogram over here focused, in a Euclidean dot. And then one over here might be 100 kilograms, but also focused, shrunk, condensed down to a Euclidean dot. Okay, so for starters, I want to say what we're picturing for this scenario is points of mass that are arbitrary in that they could be of different kilogram magnitudes. Okay, that's what if you have 2 points of mass, and so whichever one of them happens to be bigger, because they're arbitrary, right? So what's the chance that they're exactly the same size? Whichever one of them happens to be bigger, we're going to call capital M sub 1, just to keep track. Like it's not special or anything, but just to keep track of them. The bigger one, we're going to call capital M1, capital M sub 1, and the smaller, the less massive one, even though they're the same volume, the less massive one we're going to call lowercase m2. Okay, so you got these 2 dots of mass. Now we're going to imagine, this is just the setup here. We're going to imagine that these 2 dots of mass are separated by a displacement. The displacement is a vector quantity. Displacement has magnitude and direction, right? That we're going to call the displacement vector. That can be drawn from one mass to the other. We're going to call it R vector, R like as in ultimately as in radius, but we're going to call it the R vector. R is specifically designed to point from the big mass to the small mass. Okay, this is all just like set up. It's kind of like a coordinate system concern thing, like Hema. Like it's not, we're not saying that anything is special or anything like that. We're just saying this is how we're going to focus our attention on these 2 point masses. Okay, they're going to be separated by a displacement R. Okay, whose magnitude is the distance between the 2 masses and whose direction points from the bigger one to the smaller one. We're going to go one step further. In fact, this is just all the setup. We're going to call that bigger one the source mass, or the one that we're paying attention to, the one from which the displacement originates. We're going to call that the source mass. And we're going to call the other one, the other one we're going to call, for reasons you'll eventually see, we're going to call it the test mass. It's almost like the smaller one we're kind of using to test the effects of the bigger one on it. Okay. Now, if this is the setup, the claim of Newton. Sorry. What is the word after point? Sorry. Wait, there's stuff in the chat that I missed. What's the word after vector? Okay. R is the displacement vector pointing. Oh, yeah, I am an axe murderer. Sorry. R is the displacement vector pointing from M1 to M2. Wait, so did everybody get? And then, so after pointing, the word is that, so a bunch of people are, tell me if that's not clear. Okay, thank you. Okay, great. Okay. Now again, this is just all like setup, right? This is like what well, here's the claim. Oh, okay, go back for a second, please. Yes. Okay, I'll go back first. Tell me when. Okay, great, no problem. Thank you. I really like you guys. Really do pay attention. I do appreciate it. Okay. 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 First, I'm just. Oh, and there's something in the chat. Hold on. Oh, okay. All right. What I'm. Okay. So, first of all, here's this universal claim. This is a law. Okay. I'm not going to. From it, I mean, this is like a GDP, a general definition or principle or law. This claim that I'm making now, our big interest is in this class is how to use it, what it implies, what consequences follow from it. As far as why we believe in it, well, it's a law. I mean, there's a whole bunch of history and background as to how Newton came up with this. But this is like F net equals ma, or Newton's first law of motion, or something like that, where, of course, there's a history and a background of how he came to this idea. But there's not some direct proof of it or something like that, because this is the thing from which we prove other things. Okay, this is like a premise or an axiom or a postulate or a law. Okay, and it's one of Newton's great contributions to the history of physics, because it's, in a way, seemingly unmotivated. Like, it's a big leap forward to even claim this thing, and it ends up being verified and confirmed in the same way that it was motivated, which is tons and tons of astronomical data. Okay, this law, in the first place, sort of comes from watching, very carefully watching planetary orbits around the sun and lunar orbits around planets and the motion of the stars and eclipses and all this stuff in outer space. That's where this comes from. I mean, it comes from Kepler's 3 laws, which come from Copernicus. And where it leads to is all of these understandings that we have of patterns of outer space and stuff like that, because it is a universal law. It's about how mass interacts with other mass everywhere in the universe. But it's a big pivot point in the history of physics, because just to cut to the chase, this is not something I would ever ask you to prove in this class, because it can't directly be proved by analytical methods. It's the hub from which we prove other things. So what we want to get to, right? So we're going to accept it as a given, okay? That's a big enough deal. But I have to now spend some time saying what it means, what it's saying, okay? So what is this thing saying in English? This universal, this is a, well, yeah, that Apple story. I mean, don't get me started. Yeah, I mean, that Apple story is legendary. Maybe I'll have time in a few minutes to allude to that Apple story. Certainly, if you've ever heard that story of the apple falling on Newton's head, it absolutely has to do with this I think it's apocryphal. Like well, anyway, what the Apple story is trying to get at. And yeah, I think it's I think a lot of these classic stories are, see, I'm distracted. I really, how many physicists does it take to, how many psychologists, how many, it doesn't matter. All right. Anyway, how many psychologists does it take to change a light bulb? One, but the light bulb really needs to want to change. Okay. The Apple story is meant to get at this. What the law is saying, what it's asserting, what's a big deal about this law is that there's this thing called universal gravitation, right? I mean, again, to play off what Evelyn's talking about, what we had known, what people of all kinds, natural philosophers and just regular people had known for centuries before Newton, is that stuff near the surface of the earth falls toward the center of the earth. What we all know is that there's this phenomenon, this effect called gravity with a little g, by virtue of which it seems like anything that's not held in place by some upward pointing force, anything that's not held in place near the surface of the earth seems to automatically accelerate toward the center of the earth. So there seems to be this force of, so once you get, and Galileo knew that and knew a lot about them. I mean, Aristotle knew that. Everybody in a way knew that. The details of it start getting ironed out with Galileo, the numerical details, the constant, even I knew, okay, that's funny. So Dennis, you're rocking today. I think you know a lot, actually. Can you teach my son Pokemon? Anyway, right, okay, so a lot of people knew that. Galileo starts working out the details and some of the interesting properties that, like the acceleration due to gravity is approximately a constant near the surface of the earth, et cetera, et cetera. So and then Newton starts working out this idea that when things accelerate, it is due to a force acting on them, okay, right? That things don't change their velocity, they don't change the way they're moving unless forced to. But then Newton comes along and with this equation is asserting, okay, it's not a special property of Earth that pulls masses towards the center of it. In the spirit of Galileo showing us that the Earth is not the center of the universe, in the spirit of Galileo, not just in the spirit, in an extension of Galileo's principle of relativity that says, ultimately, what Galileo's principle of relativity, which we used in the Doppler effect and all of that, right? The point of Galileo's principle of relativity is velocity is not a property that one object has. It is a relation that one object bears to another, right? What does that got to do with anything? Well, it was Galileo that told us the Earth is not objectively sitting still. Just because it feels like it's sitting still. It's sitting still relative to us. We're sitting still relative to it, but it is moving relative to the sun. If you ask, how fast am I going right now? The answer is 0 relative to Earth, but 65,000 miles per hour relative to the sun, and they're both correct, right? This is the big Galileo breakthrough, is that the speed 0 is not special and planet Earth is not special. Okay, I see something interesting happening in the chat. I'm gonna look in 1 second. The big breakthrough of Galileo is that the Earth is not special. It's not sitting still any more than the sun is sitting still or Jupiter is sitting still or anything else sitting still. It's sitting still relative to itself. And it's moving relative to other things, and other things are moving relative to it and sitting still relative to themselves, right? So similarly, and I do see they're saying in the chat, I'm going to look in the chat in a second, but just to tie this together before I confuse anybody, Newton played off that or extended from that and said, okay, similarly, if Earth is not especially sitting at the center of the universe, if there's nothing special about Earth, which again is a very big revelation, right? It certainly feels like the Earth is special to us. It feels like it's the center. But Galileo's point and Newton's point is anything can feel like it's the center. Everything feels like it's the center. But Earth is just a rock moving through space. just the same way the moon or Jupiter or anything else is moving through space. So what Newton said, I'm just going to spit this out in brief, and then I'm going to look in the chat, and then I'm going to get back into the mathematics of this. Newton said there isn't some special force of gravity that's coming from the earth that's pulling apples out of trees toward the earth. Newton said any and every point of mass in the universe, any bit of mass you have, however dense it is, any kilogram over here, any millikilogram, any milligram over here, any whatever, like, or any ton, metric ton over here, every and any bit of mass is automatically all the time exerting a force of attraction on any and every other bit of mass all through the universe all the time. This is the English I'm saying. I'm going to get into the math again. Again, I'm going to get into the chat, but then the math just on a broad, and also just vaguely trying to relate to the Evelyn point. I mean, even though it was like a semi-joke, but like the point behind that image that we all have, even though I think it's probably not actually accurate, but this idea that Newton was sitting under an apple tree and an apple fell on his head and it was like, oh my, eureka, or whatever. Like, wait a minute. The thing that we're supposed to be taking away from that story is that somehow Newton realized that whatever was making the apple come down to Earth was not a special thing about Earth, that everything in the universe is actually drawn by a force to everything else in the universe. Now, and I will pause for a second, and whether he thought of this sitting under an apple tree or not is ultimately, and of course, there was a lot of data that he was working with that. I mean, it certainly did not just come to him in one moment. There was paper all over his attic about this, some of which he showed to people and some of which he didn't, and was discovered after his death. But working through Copernicus's data, Kepler's data, Tycho Brahe's data of the universe, of the night sky, I should say. Newton realized that every bit of mass automatically exerts what we're now going to call a gravitational force of attraction on to every other bit of mass in the universe. But some masses exert a stronger force on some than others do. And that's why the whole universe doesn't, or that's part of the reason that the whole universe doesn't just like all of a sudden fold in on itself, like, well, we're not all together. The magnitudes and the directions of these forces vary from pair to pair to pair according to this equation, which I'm now going to break down in a little bit more detail. But that's the overall idea, is that everything and it's a big idea. I mean, I'm yelling because I always do, but I'm yelling because this is a breakthrough. And that's why there's like an apocryphal story of an apple, because it is a big moment in science that someone would say something that looks like a very local specific phenomenon is in fact that's just our exposure to the special case of a much wider phenomenon that can be captured in one equation. Like, it is a big deal when this happens in science. And there's been modifications on this idea, especially since Einstein. But this core idea is that every bit of mass automatically, just by virtue of existing, exerts a force of attraction, that is a pull, on every other bit of mass everywhere in the universe, no matter how big or small, no matter how far. That's the details I want to get into now in a second, and the vector notation, because that R has a caret over it, and that may be a new symbol to many of you. That's what I have to sort of break down here in a second. But let me just look, something happened in the chat. 1 second. Oh, wow. Okay. Okay, hold on. I'm just going to Okay. All right. So this equation right here gives the mathematical details of this idea that every bit. So if you have 2 bits of mass separated by a displacement r, the first one is automatically going to exert a force onto the second one. And there's a bicycle in our job. Okay. Right. What, okay, just a little back. I have to give you a little back. I do see something else is happening in the chat. I'll look in a second. And I want to get to the math of this, of course, but since I feel like I'm given a little bit of permission, maybe, but to understand gravity, and remember, we're trying to remember or understand gravity a little bit here so that we can understand electrostatics. But in my experience, to understand gravity and really appreciate gravity properly, part of it is to remember what a force is in the first place, okay? The claim about gravity here is that it is a force that is universal, that anytime a mass exists at all, without doing anything, without having to try to do anything, it will automatically exert a force on any and every other bit of mass. Now, again, I'm going to keep saying that over and over again because that's like a really big thing to say. Like, if you really let it sink in what I'm saying, it's almost hard to believe. I mean, and there's a reason it took 2,000 years for anybody to believe this. Like, I am saying that, like, for starters, that like the handkerchief in my pocket, or one corner of this handkerchief is automatically right now not only pulling on the handkerchief in your pocket, which I am saying, right, even though I can't see you and I can't, right, but like, or I mean, it's certainly pulling on the handkerchief in my wife's pocket, or whatever, the pen in my wife's pocket, but it's also, if you have a pen in your pocket, it's pulling on that, but also I'm saying this handkerchief is automatically right now pulling on a piece of dust in the Andromeda galaxy. Like, I'm saying that every bit of mass is automatically exerting a force on every other bit of mass everywhere in the universe. And to remind you what a force is not a speed or an acceleration. I mean, it causes acceleration, but a force is not a speed or an acceleration or an energy or a force. Is an interaction between two thingy things, between two particles. Let me slow down for a second. Just like we were really drumming in with Doppler effect and with physics 203 that velocity is not something a thing has, it is a relation that a thing bears to another thing, right? Velocity requires two objects for it even to be meaningful in the first place. Similarly with force. Now, by the way, that's not true of everything. Like, something can have a temperature. You don't need two things I mean, arguably, or something can certainly have a mass. You don't need two things in order to even discuss mass. But you do need two things to even discuss velocity, and you need two things to even discuss the concept of a force. When I say thing, I mean thingy thing, particle. A force is an interaction between two particles. It is one particle pulling or pushing on another particle. That is what we always mean by force from the beginning of 203. I mean, from the moment we introduce it. Whether we're talking about normal force of one surface banging into another, or tension force, one end of a string pulling on another object, or the reverse, or we mean a friction force, one surface rubbing on another. A force is one particle pulling or pushing onto another. And it also means pulling or pushing in a symmetric way. Like, that's why I write here, like, don't forget about Newton's third law. If I say that I'm exerting a force on you, that necessarily means you're exerting the same magnitude force back on me. Same magnitude, but in the opposite direction. So just before I go any further, what a force always is a push or a pull that one object is exerting on another. When I say the word pull, I mean attraction, I mean coming together. When I say the word push, I mean repulsion, I mean going away from each other. I'm going to go on with this. My goal, of course, is to turn this into something mathematical. There's something in the chat, though. Hold on. Oh, okay. So, according to universal gravitation, any bit of mass in the universe will pull on any bit of mass in the universe will exert a force on any other bit of mass in the universe. But force is a vector, so it'll exert a force that has some specific magnitude and some specific direction. Let's talk about the magnitude first, because it's a little bit more straightforward. Okay. Okay, I'm going to turn the page here. So I want to break down some of the vector notation here. Again, some of it's going to be maybe obvious, whatever. It doesn't. I'm going to break down the vector notation here. So let me back up for a second. I'm going to say some general things now about vectors. Let's assume in fact, let's. Yeah. Let's assume that we have some arbitrary, so I'm backing up now to just vector language in general. So assume we have some arbitrary vector called A, right? A has magnitude and it has direction. In the old-fashioned way of talking about vectors, or the way that you might be used to from a prior physics course, A can be designated with an arrow, and the length of the arrow can indicate the magnitude, the size of the vector A, and the orientation of the tip and tail of the arrow, the angle that the arrow makes relative to some coordinate axis, can designate its direction, right? So this is just an old-fashioned, regular, arbitrary vector A. Here's some notation I want to introduce. From now on, if I just write
A triple arrow, what?
right, okay.
The-
So what I'm writing is A, if we have, this gets a little bit, picky, but if A with an arrow over it is the vector A, the quantity that has magnitude and direction, then if we're in this context where we're dealing with vectors, then from here on in, if we just see the symbol A written down without an arrow above it, right? So A, triple equal sign, what A is defined to be is the double absolute value symbol of a vector, which means in English, A without a vector symbol on it refers to the pure magnitude, or maybe that's what you can't read, sorry. The pure magnitude or the pure size of the vector A. Like, I'm being very picky here for a reason. For a minute, let me make this. I'm saying from now on, if we're in vector land, if we're in a context where we're dealing with vectors, we're dealing with quantities that have magnitude and direction, then whenever we put an arrow over a letter, we mean the whole vector. We mean both pieces of information, its magnitude and its direction. But then if we're in that context where we're dealing with things like vector A, if we just write A without the symbol above it, we're not being careless, like it's not a typo. If we literally just, and sometimes if this was all being typefaced or written or something, or in like, what do you call it? Oh my God, I can't believe I just forgot. A latex or something like that. Like a language, like that maybe instead of an arrow over the A, it would be bold-faced or something. But what I'm saying is, if we don't bold-face A, if we don't put an arrow above it, and if A is just sitting there by itself, what that means to us is, very explicitly, that we're just right now talking about the pure size of the vector A, just the length of that arrow. We're not referring in any way to the direction of it. In other words, we're not saying A isn't a vector anymore. And we're not forgetting about the fact that A is a vector. But if we just write A, when we know A is a vector, then we mean just the size of A. Now, here, okay, the double absolute values that's a way of saying, magnitude of a vector. You might wonder why they add double absolute values. Well, if you really think about it, what absolute value means with numbers, okay, I'll write this down for a second. Note, like the absolute value of -7 equals 7, right? Like everybody in the class knows that, but what does that mean? What does that really mean? Like the absolute value of a number, of some number, sorry, if you really think about it, the absolute value of a number means the distance from that number to 0. If you think about what absolute value means is a concept of treating numbers on a number line as though they were vectors just in one-dimensional space on a number line. right? So when we say that the absolute value of 7 is 7, but the absolute value of -7 is also 7, what we're really saying is picture an arrow pointing from 0 to the number 7, or picture an arrow pointing from 0, the origin of the coordinate system, to -7. What we're saying is if we were just in the one-dimensional space of a number line, the absolute value of a vector on that number line is just the size of the vector regardless of direction. Like the original idea of absolute value really does mean vector magnitude, only it was introduced to us back when vectors were so straightforward because we were only dealing with numbers on a one-dimensional number line. So now we're extending that concept and saying, but even if you have vectors in two-dimensional space or three-dimensional space, now if you have arrows pointing wherever, the magnitude of a vector still means the same thing. It means like how far away does the vector take you from the origin of some coordinate system from 0, only now we're taking into account that this is a higher dimensional, more rich concept. So we take the old idea and we just blow it up and we use the double. So the double absolute value symbol technically strictly means magnitude of vector, no matter how many dimensions it has. And what I'm now saying, which almost will seem redundant to you, this is like everything else in physics. The minute you get what I'm saying, you're going to be like, why is he even bothering to say it? Now that I get it, I don't even know, like, well, I already knew that. I'll show you why. I'm saying for notational purposes, I'm saying from now on, if we have a vector like A, we can like isolate just the pure size of it by just putting double symbols around it, or putting it just by itself. But then similarly, what we can do is say we can isolate the pure direction of the vector. We can say similarly from now on, like here's where I'm making a claim that you might, depending on what math you've taken, you might not know this. From now on, A with a caret over it, okay, which physicists, well, okay, this is the new piece of notation. Now, this is just notation. In some ways, it's, when you get it, you'll see it's in some ways very simple, but I warn you, it's simple, but it's not easy. It's meant just to be a useful thing, but it can really throw people off. So bear with me for a second, especially for those of you who have not seen this before. Or any of you, from here on in, if you see a letter with a caret above it, first of all, that caret above it, believe it or not, in physics, we call that a hat, which is ludicrous, but we call that a hat because it's like above the thing. We do. So that thing right there, A with a caret written above it, if you were reading it out loud from a textbook or a website or whatever, and you're reading to another physicist, you would read that as a hat, like literally, I'm not joking. And that's honestly the only thing that it's called. It's silly, but it's completely universal. We would read that symbol as a hat. And what it means, a hat, means the vector A divided by the magnitude of A, Okay, so the whole vector, the whole arrow, divided by its own length. So that, for example, let's say the unit vector, excuse me. So let's say, for example, the whole vector A was a vector that's 3 meters long, pointing at 45 degrees northeast, right? Like let's say this vector that we're talking about, this one over here, was 3 meters long, pointing at 45 degrees northeast. Then in order to construct a hat, or in order to understand what we mean by a hat, or define it in our minds, what we would do is take a vector that's 3 meters long, pointing at 45 degrees northeast, and we would divide it by the number 3. We would divide it by its own length. What would that give us? That would give us a vector that would be 1 meter long, right? Like duh, right? Like 3 divided by 3 is 1, not a coincidence, not an accident, and not an arbitrary example either. We would get a vector that is 1 meter long, but still pointing in the direction of 45 degrees northeast. So if this is our vector A, the unit vector A, and we would call that result A hat, we would call it the unit vector for A. So in this case, like the unit vector A is a vector, in all cases, the unit vector for a given vector is a vector that necessarily, on purpose, by design, points in exactly the same direction, but has a magnitude of precisely 1, like 1 unit, right? So it's called the unit vector. Now, bear with me for a sec. This is a construct. It's like a piece of notation, or it's an idea in our minds. It's meant to make mathematical vector language and vector manipulations a lot easier once you sort of accept this idea. And it's not a discovery. It's like an invention. Like it's like a device that we use a lot in vector calculus and in vector anything. The idea here, so what I'm talking about from now, again, for anybody who's just tuning in, I'm trying to define for you a symbol. The symbol is that hat, that caret. Whenever you see it over a letter, what we're saying is we're talking about the unit vector for that letter. In other words, anything with a caret over it is a vector. It is a vector. It has direction, some very specific direction. What direction? The direction that that letter points in. But it also has a magnitude. What's the magnitude? Always 1, by design, on purpose. So this thing, the unit vector for A is a vector that's designed to point in the direction of A, whatever that is, but only have a magnitude of 1. Now, I'm saying a lot of words, and like as usual, it probably sounds like I'm saying a lot of words and maybe not a lot of content. Like you either might be confused because you have no idea what I'm saying, or you might be like, I think I get what he's saying, but then why is he making such a big deal of it? Like what, like, is he really saying that much? You'll know, you'll get it if you see that the result of all of this, the purpose of this notation, I'm going to tie it back to gravity now, obviously, but the purpose of all this is such that Okay, here's the point of all this. It's a notation thing, but I'm going to write on the next page, obviously. But here's the thing. From day one with vectors, we've always been saying a vector is a quantity that contains two pieces of information, a magnitude and a direction, right? But if you really sort of think about it, all the ways we ever dealt with vectors in physics 1, we always said that a vector contains magnitude and direction, but then we would just keep saying that in English and doing all these things with vectors and sort of dealing with the magnitude one way with these arrows and then dealing with the direction in another way with like theta and sine of theta and cosine of theta. And we sort of were always treating them in two different things on the page. And we just kept asserting in English that vectors contain magnitude and direction, but we never had a package. We never had a symbolic way of actually capturing the magnitude and the direction in one construct or in one expression. So from now on, because we've defined this unit vector to be the vector itself divided by its own magnitude, from now on, any vector A can be regarded as its pure magnitude times its pure direction, right? Now, again, in a way, this is just a piece of notation, but it's going to condense and simplify a lot. Like we've always said in English that a vector is magnitude and direction. Now I'm saying, sure, absolutely, go back. And you should submit that for points, yeah. I'm going to keep talking, but yeah, here we go. Is it? And just let me know when I should. Oh, wait, was that? Oh, great. Okay, thank you. Okay. So what I'm saying now is it's not just roughly in English that a vector is its magnitude and its direction. What I'm saying is from now on, a vector is its pure length multiplied. So any vector is an arrow. An arrow, which is its pure length times an arrow pointing in a particular direction whose length is 1. So if the vector here is 3 meters pointing in 45 degrees northeast, then we can from now on not just say that in English, but say, okay, the length of it is 3 and its unit vector is a vector of one length pointing at 45 degrees northeast. So if you multiply 3 times an arrow of 1 pointing at 45 degrees northeast, what you get is 3 pointing at 45 degrees northeast. So this is a way that we can keep track from now on of, so it, bottom line, what I'm saying, and now I'll relate it back to the actual, it ends up being a very, you'll see, it ends up allowing us to deal with vectors in a much more straightforward way. From now on, this would be the pure magnitude of A. And this, from now on, is the pure direction of A, right? Just always remember, in other words, when you see that caret from now on, like you're going to in gravity, and like you're going to in electrostatics, and like you're going to in magnetostatics, magnetism, whenever you see that unit vector from now on, what you want to think of is, you want to remember, and I'm going to turn back to those things right now, but remember, A caret just equals the vector A, but divided by its own length. So A caret equals way of designating direction. Sorry, I always squeeze these things at the bottom. Way of designating direction without way of designating direction without altering numbers. If you see a unit vector in any equation, the first thing you want to remember is the size of the unit vector is 1. So any multiplication that you're doing won't be affected by the unit vector. The unit vector is just there to tell you direction. So let's now apply this to gravity, okay, and see what I'm saying, okay? Back to gravity. Or back to gravitation, I should say. We're saying, and I'm just going to rewrite what I had on the other pages. We're saying that there's this force vector known as gravity, which apparently is equal to the negative times a bunch of magnitudes, which of course I have to explain in a minute, a bunch of magnitudes times r hat, sorry, what was the word after alter? Oh, numbers, I think numbers, wait a minute. Yeah, sorry, I really squeezed that in. What I'm trying, that word at the top there, this got really fouled up handwriting, but that word is supposed to say numbers. So what I'm trying to say to everybody, that doesn't make it any better, but the word is numbers. Okay. What I'm trying to say is, oh, okay, you're welcome. What I'm really trying to say, look, I got to be honest, this R hat thing, it's like, it's super important. It's shockingly important if you go on in math and physics and other sciences. It comes up a lot. And honestly, it confused me for years. It really can throw people off because whenever you see an equation, if you're not used to it, people never know what to do with it. It looks very intimidating. And the first thing I'm trying to tell everybody, I'm going to give you an example right now of what to do with it. But the main thing I'm trying to tell you is if you ever see any letter with a caret above it in physics or anything you read online or like if you read any physics online or in textbooks or journal articles, if you see a letter with a caret on top of it, if it's in a physics or mathematical context, what you're seeing is a unit vector. So it's telling you something important about direction. But if you're trying to get a feel for numbers, if you're trying to do some multiplication or something, which we're about to do, and you're trying to get a sense of the size of something, whatever you see that has a caret over it always has a value of 1. That's what I mean when I say it doesn't alter numbers. And it's really easy to forget that because it's like, looks really intimidating. So if you have no takeaway from all of what I'm yammering about for minutes and minutes now, if there's no other takeaway, the takeaway is if you see R hat from here on in, R with a caret over it, first and foremost, think of that as the number 1 pointing in a certain direction. It doesn't change multiplication, but it's there to tell you something about direction. So here we go. Here's what I mean. In the case of gravity, this is the equation for gravity written in strict vector terms, right? But it's saying that force is a vector, and therefore the force vector is some magnitude times some direction. Like this is the notation we're using now. We from here on in think of a vector as an arrow of some size. And so the way we write down these arrows from now on is the size times a bunch of symbols that actually indicate the orientation of that arrow, right? And by the way, this all assumes something that also escaped me for years until it didn't. This all assumes that a vector is an arrow or can be represented by an arrow. And if you multiply a vector by a scalar, if you multiply a vector by a pure number, what you get necessarily is a new vector, right? When you multiply a vector by a scalar, you get a vector. Now think about that for a second. Like everything else, it's sort of like obvious, but it's not. It's obvious once you hear it, but you might not have thought about it before. And it's not necessarily obvious that it's important, but it is. If you take an arrow and you multiply it by a scalar, by a pure number, the whole reason that we call that pure number a scalar is because all you're doing is you're scaling up or scaling down the arrow. When you take an arrow and you take an arrow that's 3 meters pointing northeast and you multiply it by 4, the pure number 4, what do you now have? You still have you've scaled up the arrow, you've quadrupled its size, so you now have a new arrow that's now 12 meters, but still pointing northeast. You see what I'm saying? So we're saying, and vice versa, we're saying that when you multiply a vector by a scalar, what you're doing is you're scaling up or you're scaling down the vector. So you get a new vector. Therefore, we're saying that a way we can think of vectors from now on, the way you can think of any vector is the scaled up or scaled down version of a unit vector. You can think of any vector you want as just like take an arrow of size 1 pointing in the particular direction and blow it up by the appropriate size. So the force vector that is indicated by the gravity law is a vector of force. It's a number of newtons pointing in a certain direction. The number is given by everything that's in this parentheses. That's the magnitude of the force vector. What we do is we multiply all of that by a pre-existing vector, a unit vector that already pointed in a certain direction. What we're going to do is take a certain vector that's already pointing in a certain direction, but has size 1, and we're going to multiply it by a certain magnitude to get the resulting force vector. So if we want to look at magnitudes for a second, this means, so gravitational force is a vector. Gravitational force, I know I already wrote this like a couple pages ago, but now I'm just getting back to the point. Gravitational force is a vector. The magnitude of this vector, the pure magnitude of this vector, is given by, okay, so if I'm just going to talk, and I think there's nothing in the chat. Okay, the pure magnitude of this vector is given by, okay, I'm just going to look at pure magnitudes now, is given by right? That's the pure magnitude. I'm not looking at the negative sign. That has something to do with direction. I'll get to that in a minute. And I'm not looking at the R hat. Remember the R hat, which is the new piece of notation for many of us. The R hat was a piece of directional information that intrinsically, by definition, had a magnitude of 1. So I'm not writing that right now. I'm just looking at pure magnitude. According to this, sorry. Very good. Who said that? Oh, thank you, direct chat person. You're absolutely, whoa, definitely submit that for points. Sorry. Yes. I don't even, and see, it's so polite that she or he would correct me privately to save the dignity of me. I'm going to open up another portal for like dignity. Thank you. But no, she or he is totally right that, yes, there should be a squared in the denominator here. That was just my spazziness. Yes, thank you. Okay. So according to this, the gravitational force magnitude is direct. Well, I better write on the next page because I keep doing this. Someday I'll know how to budget a whiteboard. The magnitude, and I'll flip back in a second if you need, but the magnitude is directly proportional to each. Now, this is the part, after all my gobbledygook, the part that I'm writing right now is probably the one part that Professor Walters probably very quickly said to you last semester, that the magnitude of the gravitational force is directly proportional to each of the point masses, the point mass magnitudes, and is inversely proportional to the square of the distance between point masses. Note I'm saying, no, R is the is the magnitude of R vector. R hat is R vector divided by R. So in a way, again, I'm saying something sort of, well, okay, I'll slow down for a second. The thing that I'm saying on this page, and I can go back for a second if that's what someone's asking me, or was that to say? No, okay.
Yes,
Oh, just in
please.
case. Oh, should I go back? Or sorry, Chris.
Please. Thank you.
Oh, yeah, okay. Okay. Okay, I'll just pause for a second.
Yeah, you can go back to the other page now.
Okay. Okay. So we're finally sort of getting to some physical content here. In a way, the thing, maybe I'll read it out. Well, I'll read it. Okay, I'll read it out loud. I'm saying the gravitational force is a vector. The magnitude of this vector is given by the magnitude. So the size of the force that one point mass exerts on another, the size of that force is given by G times M1 times M2 divided by R squared. And I still haven't defined G yet, of course, but so what does that mean? According to this, the gravitational force magnitude is apparently, according to this equation, assuming that capital G letter, which I haven't said anything about, but assuming that capital G letter is a constant, assuming it's some kind of which it is, assuming that that's some kind of constant. So assuming that the independent variable is R, lowercase r, and the dependent variable is F, then what, according to this equation, then the force that one point mass exerts on another, the force magnitude, is directly proportional to each of the point mass magnitudes, right? We're just saying in English, we're saying the heavier either or both of these point masses are, the bigger the force of gravitational attraction one will exert on the other. So heavier things automatically pull more on other things. That's what we're saying so far. And we're saying that the force magnitude is inversely proportional to the square, thank you, direct chat person, of the distance between the two, right? In English, we're saying that for any dot of mass over here, separated by some distance from some other point mass over there. And again, these are both points, like they don't have any volume, but they have different amount of kilograms. They have different densities. So they have different massivenesses, right? Anything over here automatically pulls on anything over there by an amount that gets bigger and bigger as either one of these gets bigger and bigger, and gets smaller and smaller as the distance between the two of them gets bigger and bigger. That's what we're saying in English so far, just about magnitudes. And yeah, we're specifically saying when we put R squared in that denominator, R squared, notice it's not R arrow squared, and it's not R caret squared, it's just R squared. What is R? R is the magnitude of the R vector. R, in other words, we're being careful now. R vector is a displacement, but R is just its magnitude. And what do we call the magnitude of displacement? We call it distance, right? So what we're saying is the farther apart these two things are, the less they pull on each other. And in fact, it's inversely proportional. The force is inversely proportional to the square of the distance, for reasons we have to ultimately get into. But right now, it just apparently seems to be a discovery that if you make the sun and the earth twice as far apart from each other, then the sun will but all other things are held the same. If the sun were to suddenly get twice as far from the earth, it would start pulling on it. I almost should ask in the chat. Should I? I will. Let's just say all other things were equal, but suddenly the earth, according to this, were twice as far away from the sun as it used to be. The force would drop down by how much? Just put in the private chat or the public chat. I'll say the question again, just to make sure we're all together. Or you could say,
How much? Twice?
Well, I'll repeat. I'm not sure I agree. If the sun, according to this, the force is inversely proportional to the square of the distance. So I think
No, I just want to hear you to repeat. I just want you to
Sorry.
repeat.
Sorry. Okay. So I'm saying, let's say the Earth were suddenly twice as far away from the sun as what it usually is. Then the force would reduce by what factor? I'll repeat it again. Okay, and everybody's going in the direct chat because you're so polite to her. Cool. All right, wait, hold on. I'm not gonna respond to everybody in the direct chat, but cool. If you're in the direct chat, I'm psyched. Hold on. Actually, I'm gonna repeat the question again just to make sure that everybody. I'm going to repeat the question. So some of you in the chat are right and some are wrong, honestly. And again, remember, you could submit these for points either way. And in fact, if you're wrong, you can even submit for additional points for being wrong, as weird as that is, because I know everybody's trying and you're not janking the. So let me say again, look at the equation. The equation says that the force is inversely proportional to the square of the distance. So if we made the distance twice as much, I'm seeing more answers in the chat. That's good. I'm going to wait for like 2 more answers in the chat and then okay, cool. And I see some modifications in the chat. Cool. But I'll just say one more time, and everybody should try, even if you don't put in the chat, and look, everybody's in the direct chat. So you're not in a race and you won't be embarrassed. And I'm telling you right now that some people are already wrong, which just makes me feel like I'm not wasting your time. Nobody has put in the chat like a fish. I mean, nobody's put in anything totally crazy and like surreal. Everybody's on the topic in the chat. So you're just proving to me that you're paying attention and you're with me. But if a few of you are getting it wrong, that also just proves to me that I'm not wasting your time. So don't be embarrassed and don't worry about it. Like serious. And that's why you get extra points for being wrong sometimes, because it like help. Okay. So I'm going to say one more to a fish. Okay. Someone put in a fish. That's funny. Which also shows that you're paying attention, and you just got more points for being okay. Close. So I'm going to say it one more time, and just try it if you feel like it. I'm saying, according to this equation, wait, and I think it's not on the board anymore. Is it on the board? Yeah, it is on the board. All right. According to this equation, or according to the English of this equation, and yes, I think this is probably the one part that Professor Walters probably tried to teach, but probably taught very, very quickly. So this is one takeaway we want to get straight before we go on. We are saying force of gravity is directly proportional. Let me back up for a second. It's directly proportional to mass. So for sure, if the sun suddenly doubled in its mass, and everything else were equal, if the sun and the earth were stayed the same distance away from each other, but the sun doubled in its mass, then the sun would start pulling on the earth with twice as much gravitational force. That's one thing this equation is saying. It's also saying if the earth doubled in its size, then the sun would pull on the earth with twice as much gravitational force. By the way, Newton's third law is also true. So anything I'm saying right now about what the sun is doing to the earth, I also could be saying about what the earth is doing to the sun. It's all happening at the same time. I'm just like focusing on one direction at a time. Okay. But if the sun doubled in size, in mass, then the force, the pull magnitude that it exerts on the earth would double. I'm asserting that. That's what direct proportionality in the numerator means. But now in the denominator, we have R, and not just R, but as someone pointed out, we have R squared. So think about so I'm saying the force is inversely proportional to the square of the distance between them. What you want to know, and it's not obvious, it's just we want to make it clear, is that means if all of the things were equal and the distance between two objects, two masses were doubled, what that means, I'm going to assert the answer right now. I'm going to look at, okay, what's the question again? Okay, cool. Okay. So someone's asking, what's the question? So the question is this: if we doubled R, if we doubled the distance between M1 and M2, if we doubled the distance between the two masses, but we left everything else the same, what would happen to the force the gravitational pull exerted by one mass on the other? That's the question. I'm just going to say what, right? And I have a lot of answers in the chat now. Most of them are actually correct. Some people have changed their mind. That's cool. I can't respond to all of them because there's so many, which is great, but just people that. Okay. So I'm going to say, it looks like a lot of people have modified their answer enough that I think people are with me. So yes, the answer to everybody, and again, please, whatever you did in the chat, please submit it for points. Really, it helps the class so much. You deserve the point. And I don't want to spend the time now to respond to every single one because it was a quick enough question, but just okay. So the answer is yes, good. Whoever just went into the direct chat, yes, absolutely. And in fact, I'll even say like the last 4 people in the direct chat, I think got it right. So the answer is yes, the force would go down by a factor of 4. Like it would go down to, in other words, 1/4 of what it originally was. Now, I don't care if you got it right or wrong a moment ago, but I do care that you understand it now that I'm going to say it. Like, even if you're like, oh, duh, oh, that's what you mean, fine. But what I'm saying is, if what inverse proportional to the square of the distance mean, in fact, I'm going to say this really explicitly because this is known. This is an example. The whole reason I'm making a big deal of this is like there's tons of forces in physics based on this mathematical model. I promise I'm not trying to waste your time. Anything we're saying about gravity here is going to carry over to electrostatics, and it's going to carry over to magnetostatics, to magnetism. This type of force is called an inverse R squared force. If the example, if the R between 2 points is, I'm just going to give a new example right now to make it as clear as possible, is tripled, then the force reduces to 1/9, right? That's a different example, but you'll see, just to make sure that you can see in your head whether you're getting what I'm saying. I'm saying if you multiply the R by 3, then the whole force goes down by 1/3 squared, which is 9. So 1/9, right? The bigger the distance, the smaller the force, but as a function of the square of the distance. So it's a very dramatic effect, in other words. If you double the distance, then the whole force goes down, but not by half, by 1/4 is what we're saying. And a lot of you put that in the chat. I'm just making sure. And when I'm going to say it one more time, I'm going to make sure before I go on, since there was just enough. And so if you put 1/4 in, yay. But if you put anything else in, no shame. But let's make sure before I go on. Well, in fact, okay, I'm going to change this. I'm going to ask her. Hold on. I'll change view so I can see you better for a second. Can you just, if you get it now, oh, great. So one person in the direct chat just did what I was going to ask. And regardless of what you thought a minute ago or last semester, can you please honestly put up an electronic hand or something if you get it now, what I'm saying about inverse R squared? Cool. Oh, and the sounds kind of the animations. Oh, it's so satisfying. Okay, awesome. In fact, now I'm going to do the test, the control of the experiment. Wait, now keep them up, because I don't want to single anybody out for not understanding. But can you just now raise your hand if you hear me speaking at all? Raise an electronic hand if you hear me speaking at all. Raise your hand if you see me, if you hear me speaking at all. Please, if you're alive, please raise an electronic hand. This is the closest I get to being obnoxious. Wait, so 3 people are not raising. I'm not going to single them out by name, but if you hear me at all right now, please raise an electronic hand if you're in the room, if you're alive, if you're with. Okay, well, we just learned something. I'm going to take one more opportunity to say, if you don't want to slow down the class or embarrass yourself, I totally get it. But if you didn't get what I just said about inverse R squared, please send me direct chat right now, even if I can't deal with it now. If you're willing to just let me know or text me later, it's okay. but I would like to know because I'm assuming, but okay. All right. I'm assuming. All right. Now that's all. Now you can put down your hands. Thank you. And those of you who put up your hands to say you're paying attention, that really helps my life. Okay. Now, everything we just said, is about magnitude, and we're almost now about to go, and we're able to separate magnitude and direction more easily now with this new notation, right? Like the point of the notation is to be able at any given moment know whether we're talking about pure magnitude or pure direction of the vector, in this case, the force vector. And thank you again for keeping your hands up. You can totally put them down now if you want, unless you have a question. But there's one more thing I have to say about magnitude. Like, so if again, with magnitude, thank you. We are saying this, right? That's just magnitude. G is known as the universal gravitational constant. You don't have to memorize it. You just have to be comfortable with it. It's a number. So you have to know that it is a number that never changes throughout the whole universe. Okay. So it's constant anytime we apply this equation, and it's constant from one equation to the next. So it's even more constant than like the K of Hooke's law or something like that. And what it is, it's approximate. I'm not saying approximate because I don't know. I'm saying approximate because it's digits. It's like pi. I mean, the digits go, as is the case with all natural numbers, measured in the metric, in the SI units, whether Planck's constant or any other, the digits actually go on forever without repeat or pattern. So we have to chop them off at some point. So it's technically an approximate, but here's what the number is. It is 6.6. Oh, I'm going to look in the chat in 1 second. It's 6.67 times 10 to the negative 11 newtons meters squared divided by kilograms squared. Now, you don't have to memorize that. It would always be given on any exam or anything where we ever use this. But you do have to know that you could memorize it and you would never be wrong. It never changes. The thing to know about it is first of all, note that it's tiny. It's tiny. It's a negative exponent. It's 6.67 times 10, and then you move the decimal point 11 places to the left. So it's an incredibly small number, which means that when you take typical masses and multiply them by other when you have a typical mass that's near another typical mass, like a kilogram near another kilogram separated by a meter, the gravitational force exerted by some mass on some other mass separated by a normal, everyday, like earthly distance, by the time you're done multiplying one mass by the other mass, dividing by the distance squared, and then multiplying by this number, you get an incredibly small number. So gravity, so I'm saying right now, like, you know, like I said before, the pen in my pocket is pulling on the pen in my wife's pocket, who's upstairs in the house, right? But with a tiny, tiny number of newtons. So even the number of newtons that's being exerted by the friction of her pocket on whatever pen is in her pocket is enough to balance out or overwhelm whatever gravitational force I'm exerting on her right now. I mean, not to be weird, but just for the first thing to notice that if the gravitational forces by themselves are very, very small, they don't start mattering or being like competitive or measurable or relevant in the universe until you get really, really big masses like planets and stars and moons. Okay, and you get these really, really big masses in outer space where there's not a lot of other things going on. There's not a lot of friction or contact or whatever. So the first thing to know is that gravity doesn't really start having a huge effect until it's things like Earth pulling on apples or pens or whatever, or Earth pulling on moons or suns, etc. That's number one. And the number two, and I know there's something in the chat, I'll get in a second, but the number two thing to notice about this number is the units may look very, very obscure. They might look to you like the hardest thing to memorize in this number, like newtons times meters squared divided by kilograms squared. But actually, if you stand back and look at it, the units are not only make total sense when you think about it, but the units are actually the purpose of that number in the first place. If you look, and I will get the person in the chat in a second, of course, it'll be completely moot by the time I get there, but those units, they look all weird. But what we're just saying is the units of the 6.67 number are meters squared. Why? To cancel, like meters squared in the numerator, to cancel out the meters squared that are in the denominator of the force function, divided by kilograms squared to cancel out the kilograms that are squared in the numerator of the force function, right? So all of that obscurity, meters squared over kilograms squared, is just saying we cancel out all of the units that we plugged in. And then after we've canceled out all those units, then we multiply by newtons. So the whole purpose of this number is just, it's a proportionality constant that after we input all the data, after we input the independent variables of mass and distance, then we scale them up by this number and scale the units so that at the end of the day, what we get is a force measured in newtons in the appropriate SI units. This just means that at the end of the day, the gravitational force that is exerted by any one object on any other is once it's calculated, once it comes about. I mean, it comes about in this strange way called universal existence. Like it comes about automatically. If you exist, you exert gravity on anything and everything else that exists. But once we plug in the numbers and find out how much you're pulling on anything or everything, then the pull that you're exerting acts like a regular everyday pull measured in newtons and will get plugged into our general force relation also from Newton, that F net equals ma. In other words, the gravitational force comes about in kind of a strange way, but then it acts, it behaves and is measured in units like any other force in physics. It's measured in newtons. So those are the two things to note, and that's the number ensures that. We wouldn't even need this gravitational constant. We wouldn't need this universal proportionality constant if we were willing just to plug in the numbers and just get answers that were instead of in meters, kilograms, and seconds. If we were willing to get out numbers that were like in other units, then we wouldn't even need this. But okay, it's just a scaling factor, in other words. Okay, I'm going to look at the chat. I know I'm talking a lot. Well, hopefully this is, maybe I took Christopher too seriously, but hopefully this is filling in some gaps from last year. Okay, let me look at the chat. Sorry. I can go back to, yes. Wait. There's like 3. Wait, sorry, there's a lot going on in the chat. Sorry. Hold on. First of all, let me go back. Okay. No, thank you for asking. I can always go back. Then if you, yeah. Okay. So a couple of good questions in the chat. I mean, one was, can I go back? All right, so I've gone back and let me know when to go back. I mean, when to go forward. But now there's 2 questions in the chat. And again, one of them might have been sort of meant as a joke, but I'm going to take it seriously because I think it's a real. Well, I'll go in opposite order of these questions. Okay. All right, good. So yeah, okay. So one question. Well, let me do one first. One question says, can this force or this pull be applied to us or people as masses as well? That's yes. I want to emphasize to everybody, one of the reasons I'm talking about this so much, and partly because I want to introduce this math stuff, but also like this is a very big deal because it applies to everything. This totally applies. It does apply to people, like really, really. And it does, what this really applies to, like the equation itself, and then I'm going to get to the Apple question in a second. But the equation is about any M1 and any other M2. So any 2 bits of mass you can imagine. The equation applies to 1 pair of bits at a time. So it's easiest to think of this equation as applying once at a time to like 1 electron in me, pulling on another electron in me, or I mean, it doesn't have to be electron, but just like whatever the smallest particle you can imagine. Let's say neutron, right? Like smallest particles you can imagine is what this equation is first and foremost picturing. It's picturing like a neutron somewhere in me and how that neutron is pulling on some other neutron in me, or some other neutron in you, or some other neutron in some other person, or a neutron like way on the other side of the galaxy. Now, and the reason I'm saying neutron rather than person is I'm just trying to emphasize that when you plug the numbers into the equation, in the first instance, you're just supposed to plug in numbers for one bit of mass and another bit of mass like at a time. So you picture really, really small things. But if it is applying to any neutron in a person, which it is, and it's not applying to neutrons in people any less than it's applying to neutrons in stars or planets or whatever, like no neutron is special. Like that's kind of like a big point of this whole thing is no bit of mass is special. So this equation is about some kind of neutron that's like in the earth or a neutron that's in a star or a neutron that's in your body, like literally. And by the way, I'm saying neutron on purpose just because I don't want to get bogged down in issues of electrical charge or anything like that, because like that's the next equation. But so anything you can picture as a really small, or like a hydrogen atom, whatever you can picture as the smallest thing that exists, or quark, if you've ever heard of a quark, whatever, anything that you can picture as a small bit of mass that exists anywhere, this equation is absolutely applying to. And if that bit of mass is in a living creature, absolutely, still, this is applying to it. And now the thing is, to go one step further, if it's applying to any neutron in a human being or in a brick house or in a planet, then it is applying to every neutron. So it absolutely ends up being the case that all the neutrons in your body are pulling on all the neutrons in your husband's body or your father's body or your mother's body or like whoever, whoever you are, right? It's applying to everything all at once, but like one at a time. So the sum total of, and since everything is doing this, and since there are also other forces in the universe, not just this one, we get to them next, since this isn't the only force in the universe, the reason like you're not going, whoever asked this question in direct chat, right? Like the reason your whole body isn't like right now flying towards like Barack Obama's body or like whoever is because in this, even though Barack Obama's body is like pulling yours to him, and I'm not trying to be weird, I'm just using examples, even though Barack Obama, wherever he is right now, is like, or Donald Trump, like whoever, if that's pulling on your body right now, well, still by random statistics and probability, there's also some other government official like on the equal side of you, on the other side of you, also pulling on you, if you know what I mean. Like everything is pulling on everything. And there's other forces that are also repelling and pushing us away. Those come from the electrons and they ultimately create this thing called friction. So there's a lot of things happening at once. So only the big forces end up dominating, like the force from the earth to my body pulls me down to the earth more effectively, and nothing balances that out. The earth pulls me down to it more with more strength and more newtons than you pull me toward you, because you pulling me toward you horizontally is like being balanced by other forces. So what I'm saying is, yes, first of all, I'm saying this is truly universal. If this were the only force in the universe that acted this way, if this were the only universal force, everything would crunch in on everything. The whole universe would collapse in on itself if this were the only, like this is a glue. It pulls things in the universe together. If there was nothing pushing anything apart, we would all crunch in on oneself. So that's, I don't know if that's like sort of answering what one person's asking, but then what someone else, and there's more in the chat. Oh, great. Thank you. Awesome. Now, but that's a great question. Now, someone else is asking in the chat, and this is worth, someone else is asking in the chat, if there were two apples at two ends, opposite ends of the universe, and they like were at rest, according to this, if this is true, if two apples at opposite ends of the universe would automatically pull on each other through gravity, which they would, which I'm saying they would, yes, if there's two apples on opposite ends of the universe, each apple would exert a force of attraction on the other, it would, and then according to F net equals ma, like F net equals ma, so if these two apples were the only things in the universe, if there were no other objects or no other forces, right? And that's a very important if. But if there were two apples isolated at rest at two opposite ends of the universe, according to this, oh yes, they would each pull on each other. Therefore, they would each start accelerating toward each other. And even if they started at rest, they would accelerate. So they would eventually move in toward each other. Absolutely. That is totally what this is saying. Wait, I'm just looking in the chat. But F net equals ma. So things accelerate at a rate that's determined by the sum of all forces on them at once. And this is not the only force in the universe. The other big one is what we're getting to next. It's the force. So this is a force between any two bits of mass. Just to cut to the chase, the force we have to look at next, which really is like the rest of this course, is the force between any two bits of charge. And it works the same mathematics. That's why I'm emphasizing them. But with charge comes in two varieties. There's protons and there's electrons. There's positive charge and negative charge. So charge, if it's like charges, if it's opposite charges, they pull on each other like this. But if they're like charges, they push away on each other. So it turns out that the electrostatic force, which both glues and separates the universe, turns out to play an even bigger role than this. And it turns out to have, it's the constant that governs the electrical force is a lot bigger than the constant that governs the gravitational force. So we are held in balance in the universe. Okay, so these are good. So I want to get to that other one. That's really the point. But so everything I've said here is about magnitude. Let me get back to direction, hopefully very quickly, and then we'll get to the electricity. We said gravitational force is a vector and it's equal okay, so here's where this notation comes in now. Like it's all physics. It's like simple, but it's not easy. And when I say simple, what do I mean? I mean, it's not a lot of details, but like you got to get your mind around the details to make sense. So we said, so I don't know why I just did that. So everything in the parentheses is magnitude, right? It's a scalar. We take some vector and we scale it up or down by that magnitude to get the ultimate force vector. What vector do we take and multiply up or down by that magnitude? Well, apparently we take this r hat vector. Like this thing is direction. It's the unit vector for r. So what this is really defined right there. What we're really saying is, remember, r is a displacement vector that points from m1 to m2. R is the displacement from m1 to. Hold on 1 second. Hold on 1 second. Wait, this, it does go to 645, right? Yeah, okay. What I'm saying is, you picture this displacement pointing from M1 to M2, right? And it's like some number of meters. It's some huge, if we're talking about the sun and the earth, it's some huge number of meters. Then our hat is defined by, to be that displacement divided by the distance, right? That all sounds cockamamie, but we're saying if our hat, I'm sorry, if our arrow is I can't even remember that. Oh my God, I'm losing my mind. Sorry. I can't remember in meters, but in miles. If we're saying that our arrow is the distance from the sun to the earth, which in miles is 93 million miles, okay? Pointing in a certain direction, then what our hat is a vector that points in that direction, that points from the sun to the earth, but only has 1 mile of distance on purpose, right? So we take this vector, our hat, we take the vector that only has a magnitude of 1. We take the vector that points from the sun to the earth, right? And so it's a vector that's measured in distance units, really like meters if we're in the metric system, right? So our hat is in meters. Then we multiply it by all the numbers that we got in the parentheses, g times m1 times m2 all divided by r squared. We multiply by all that stuff. So okay, I'll get the chat in 1 second. So we take this number, so we take this 1 meter that's pointing in a certain direction, we multiply by all those numbers, turn the crank, and we get a number of newtons now pointing in a certain direction, right? And then there's a negative sign. This is maybe the punchline of the whole thing that I've been trying to say for 2 hours. Then there's a negative sign. Why is there a negative sign? Because the negative sign says flip the vector, right? Flip the vector. The vector was pointing from M1 to M2. So, and it was a vector that was just literally size 1, like our hat. It doesn't have a size, it has size 1, but it has a direction. What direction? The direction that points from M1 to M2. We take the vector that is size 1 pointing that direction. We scale it up by the g, by the m, by the m2, divided by the r squared. And all this scaling changes it, makes it some other number, and changes all the units and turns it into newtons now. And then the negative sign says, so we still have a vector though, right? We have a vector of a new size, still pointing from m1 to m2, like pointing from the sun to the earth. And then the negative sign says, flip that vector. And I'm going to tell you why in 1 second if you don't already see. But if you don't like that, if I lost you in the gobbledygook of GM1, M2, R squared, you could do it in another order if you like. I mean, multiplication is commutative. So you could say there's a vector that's pointing from the sun to the earth. There's a vector that's pointing. It's called R hat. It has a size of 1, so it doesn't change magnitudes, but it's telling us direction. It's pointing from the sun to the earth. The negative sign says, flip that, yo, flip that. 180 degrees, have it now point from the earth to the sun, and now scale it up or scale it down by the g, the m1, the m2, the r squared. And what we get at the end of the day, and I'm going to get the chat in 1 second, but what we get at the end of the day, what this says is the direction of f, i.e., the unit vector for f, if you're following all this, points from M2 to M1, right? The direction, this says direction. And I'm going to get the chat in 1 second. But all what I'm saying about, if you're following, and hopefully you are, I'm trying to say that the reason, if you've seen this equation before and you think you've already always understood basically this equation, or you get how the magnitudes are working, but you're like, that R hat thing is like a little annoying. Like, what's going on with that? Oh, is that a hand that's up? Wow. Wait, I'm sorry. If that's a hand that's up, hold on. It just flashed. Sorry. 1 second. And I know there's something in the chat too. Let me just spit this out. And then if there's something, it felt like a hand went up. But If there is, please let me know in the chat. But I'm trying to say, look, if this has been 2 hours of like super boring stuff that's ultimately about R hat, I mean, that may be true. I may be talking for 2 hours about that R hat, but honestly, I can't, R hat held me back in physics for like for years. I didn't understand it. And any problem that ever had it in it, I would like lie to myself and run around or ignore it or just get all clogged up. There's something about R hat that really holds a lot of, and I'm not dumb. It holds a lot of people back. So if I'm spending 2 hours here to take away what I'm trying to say right now, what the R hat is doing in this equation is it's not affecting the numbers. If it looks like it would cancel out with the R squared, it doesn't. It doesn't cancel out with the R squared because it doesn't have the same value as R. It has a value of 1 because it's a unit vector. But what it's telling us is a direction. It's a way of saying, I mean, the force is a vector. A vector is an amount times a direction. The direction of this vector, of the force vector exerted by the sun on the earth so the vector of the the direction of the gravitational force exerted by the sun on the earth, according to this equation, if you really are following the symbols, it's saying something that I know you know. I know you when I say it, you're gonna be like, oh, that's it. But see if you can see how it's expressed by these symbols. What I'm saying is this: the gravitational force exerted by the sun on the earth points in the direction from earth to sun. Like what the symbols are saying is, picture a display. If you want to know what the sun is doing to the earth, picture an arrow going from sun to earth. That's a displacement from sun to earth. And then multiply the size of that arrow so you get the right size of the force. And then flip the arrow. That's what the negative sign is saying. The negative sign is 100% about direction. It's saying flip the direction of displacement from sun to earth. If you want to know the force exerted by sun on earth, take the displacement from sun to earth and flip it so that you see that the force, the gravitational force exerted by sun on earth, is actually directed from the earth to sun. In other words, what I'm saying is, the direction of F vector, i.e. the direction of F, i.e. F, points from M2 to M1, i.e. the negative R hat means all of what I'm saying, all this 2 hours, okay, is meant to ultimately say means pull, or in other words, attraction. What I'm saying, and I will look in the chat in 1 second. I'm saying, in the end of the day, the magnitude of the force of gravity is gmm over r squared. The vector of the force of gravity is negative gmm over r squared times r hat. The negative sign and the r hat together, if you really think it through and you really understand those symbols, what they are together saying is that the force that the sun exerts on the earth pulls the earth toward the sun, which of course you always knew. I'm not saying you didn't know that. You know that gravitation is a pull. What I'm now saying is, from now on, anytime you have any kind of force like this called an inverse R squared force, if you see a negative sign, what the negative sign is denote, and you see a unit vector, but the meaning of the unit vector taken together with the meaning of the negative sign ultimately always means, I'm going to write it again, this means attraction always from now on, and this will mean repulsion from now on. And you can see why this is going to be relevant to electricity. Attraction means pull, repulsion means push. Right? That's what this means from now on. And again, I'm going to pause in a second. I know it's 6:10. I'm going to look in the chat. But I'm going to say again, just because I know some of you I've lost in the complexity. Some of you I've lost in the boredom. I totally know, and I don't want to, but I'm sure that's true. But if you're going to tune in now and get the takeaway, or you want to test whether you've gotten anything out of this class, I mean, if you want to test it in your mind, I'm assuming you do know that gravity is a pull. I think you know that. I think you even also know, or from chemistry and stuff, that like protons pull on electrons and protons push on other protons. What I want to say now is that we can keep that all straight very rigorously and explicitly and consistently with negative signs and positive signs. I'm saying from now on, negative means attraction in all these kind of forces, these universal forces, and positive means repulsion. And it works like that as long as you understand in the first place that R points from one thing to another thing, and R hat is the direction of R divided by its size. I'm ultimately saying, once you know this notation, it makes sense that negative means attraction and positive means repulsion. I'm actually going to say one. So it's not new knowledge, it's new notation for that knowledge, but hopefully will allow us to use the knowledge in a much more direct mathematical way. I'll also point out one other thing, and then I'll look at the chat. Also note, this whole system works. The system of directional notation works because a positive times a negative equals a negative. A positive times, a negative times a positive equals a negative. A positive times a positive equals a positive, and a negative times a negative equals a positive. So what? Well, think about it, right? You'll maybe I'm jumping ahead, but when we apply this exact same system to an equation that has exactly the same form, just different numbers, which is what's going to happen in 1 minute for the last half hour of class, when we transfer this over to charges, which come in two varieties, where you have instead of an M1 and an M2, where you have a Q1 and a Q2. Well, if the Q1 and the Q2 are both the same, if they're both positive or they're both negative, you're going to multiply them together and get a positive, which means repulsion. But if they're different, you're like negative and positive or positive negative, and you multiply them together, you're going to get a negative, which means attraction. You see what I'm saying? So hopefully this makes some sense. So this is whether I was just giving you a little speech about gravity or I was giving you a speech about vector notation to make sense. Hopefully this makes some sense. I'm going to pause, look in the chat, and then I'm going to see if you're okay. And then I know we have a half hour. I'm going to apply this to electricity, but let me look in the chat. Okay. Oh, good question in the chat, which I'm definitely planning on answering. I'm planning on answering it right now. Okay, good question in the chat. Well, I'll just say, okay, so I'm going to do much more on this in like a day. Someone said in the chat, I don't know if I said anything about it, I didn't, but is lowercase g a vector? Like g as in 9.8 meters per second squared. So the quick answer is yes. I mean, we often have not acknowledged that to this point, but lowercase g is a vector. Yes, it is. And we're going to get to that in all of this. That's a great question. And honestly, what lowercase g, I'll just say really quickly, lowercase g is capital F sub gr. Well, I'll just say it. So but we're going to totally get to that next, like tomorrow, actually. But just so satisfaction, what the vector this is equal to. Oops, sorry. I'll explain this more tomorrow, but literally lowercase g vector is that entire F vector, the entire vector of the force of gravity divided by the scalar magnitude of one of the two masses, generally the test mass, the second mass. So it's that entire vector divided by a scalar, which just gives you a vector pointing in the same direction, but of a different length. I mean, so yeah, and I'll explain why. You could sort of see if you multiply both sides by m2, in other words, force of gravity equals mg. And right? Force of gravity equals m. So the person who's asking, great question. I'm going to elaborate more tomorrow, but yeah, the force vector of gravity is actually the scalar known as lowercase m times the vector known as lowercase g. Yes, and maybe just acknowledge in the chat if I just did answer, because that is a great question. I don't know if you heard my answer, but okay, I'm going to go acknowledge, please. Okay. Thank you. All right. Now, I know this has been a long class, maybe a dreary class, although well, let me just pause for you. I'm not asking, this isn't Amazon, so I'm not asking whether you like the class, because even I know this is a lot, or it's like a little, I know it's like I don't know if you feel like you learn, but even if you don't feel like you learned anything exciting, can you just raise your hand if it's clear where we just landed? Is it sort of clear where we just, okay, cool. Awesome. Okay. Great. And if privately anybody like Chris is like, if they're like regretting, like, oh, that's very nice of you. Wait, I don't know if you're joking or just being super polite, but okay, I totally appreciate that. Okay. But I will just admit, if I were Chris right now, or one of Chris's, I'd be thinking like, well, that's the last time I ever ask Yabbermap to elaborate more on something. Like next time, let me just remember to, because, even if you all hadn't asked me, I probably would have gone too crazy anyway. And it's probably always a risk, but no, I do appreciate that you admit, no, oh, okay, cool. Okay. Awesome. No, I'm glad. And as long as it's clear, good. And yes, but I'm glad you've seen me. All right, I'll shut up. All right, cool. But now what's the point of all this? And well, gravity is a really big deal. Okay, I guess no, I don't. I'm going to go on to connect this, and you can put your hands down now, unless you have a question, definitely you can, where this all goes though. This is going to bring us to electricity now. And then, of course, what I have to do is then show you, I can't today. Today, the goal for the next 20 minutes is to connect this back to electricity. But then, of course, then the next goal of like tomorrow and the remaining is to show you why electricity is such an unthingy thing, right? The whole class ultimately is about unthingy things. Where we left off last Wednesday was on the unthingy motion of waves, right? Now we're into electricity. Electricity is a whole other kind of, right now we're into gravity, which gets us into electricity, which is a whole other kind of unthingy thing. I just want to remind you, never forget that to keep our eyes on the prize of this class is like we're talking about how we're ultimately always concerned about how not objects, but information flows from one place in the universe to another. Now, right now, talking about gravity, it still seems like I'm still talking about things. I am. Right now with gravity, just like in order to do waves, we have to first back up to like masses on springs, and we have to build waves from little things on little springs and like get a bunch of them to oscillate a lot and together make this big phenomenon called wave propagation, right? Well, similarly now, if you kind of understand how one massive particle automatically pulls on another massive particle, it turns out that any two points of charge will exert forces on each other. Well, forces, sorry. Remember, and a force, what is a force? Just like before, a force is a pull or a push. Okay. So, and sorry, you can put your hands down unless you still have a question. You don't have to, I suppose, but okay. Feel free to put your hands down unless you have a question or should. Okay. Okay, cool. Thank you. I just want to make sure I'm not skipping any question, but okay. Okay. So the reason we said all that stuff about gravity is that we broke down that equation because that exact same type of equation, that same mathematical form, governs whatever happens if we have any two bits, points of electrical charge, electrostatic charge anywhere in the universe. If we have a bit of charge Q1 and another bit of charge Q2, and if they are separated by a displacement R, okay, so given two point charges. Now I'm going to try to discuss what that means in a second, but nobody really knows what that means. Given 2 point charges, then it turns out, according to something called Coulomb's, and you may know this from chemistry, Coulomb's law of universal electrostatic interaction, or electrostatic force, same thing. It turns out there's a force exerted by any 1 point charge on any other point charge that could be positive or negative, equal to magnitude of a certain constant, which we'll define in a second. So, but a constant times the magnitude of one charge times the magnitude of the other. Oh, I'm writing this too big. Sorry. It's not wrong. I'm just making more space. Okay. Magnitude of one charge times magnitude of the other charge times constant of proportionality all over the square of the distance between them. So this is another inverse R squared law, hence our concern, times the unit vector R that points from one to the other. So you see, hopefully you see, this is not the same equation, but it's an equation with the exact same form as the other. R still means the same thing, like R hat still means R vector divided by R magnitude, and R vector points from the big charge, which we might call the source, to the smaller charge, which we might call the test. And again, this is all just like sort of how we're looking at it, like our frame of reference. Anything we say about what big Q1 does to little Q2, like also it's true that Q2 is doing that to Q1. We're just like trying to define our terms so we know what we're talking about when we're talking about it. So if you're looking at the force that Q1 applies or exerts on Q2, it's given by this equation. It's an inverse R squared function. Again, very interesting coincidence. It's not a coincidence, but it's very interesting to see. And we have to talk about why. But first, let me break it down again, just like before. Like, okay, like first of all, we know what R, we already defined R just like before. But what's K now? K sub E, because why sub E? Because this is our third freaking K in this class. I mean, believe me, it's as annoying to me as a teacher as it is to you as a student. We've had 2 other Ks already in the class. K, which means that, plus you have a K in chemistry, I know, but they're all different Ks. I'm sorry that they're all called K. But the first K in this class was the K of Hooke's law, spring stiffness, measured in newtons per meter. That's one thing. Then the next K was angular wave number. That's measured in radians per meter, totally different thing. I tried to distinguish them by putting serifs on the second K, or you could have made one lowercase and the other K, I don't know. But then this one is a third one, completely different, has nothing to do with the other 2 Ks. We put an E, I mean, books will do different things, but I put an E subscript on it to indicate that what I mean by this K is you either call this the Coulomb constant, named after the man who came up with this whole law, Augustin de Coulomb, a French physicist and chemist from the late 19th century, or late 18th century. The Coulomb constant, or you could call it the electrostatic constant, same thing. This whole law can either be called the Coulomb law or the electrostatic law. It's all about the electrostatic interaction between any two charges. That's what this is all about. See, whatever names imply that. And what it is in numbers, okay, it's just a constant. It's the same, you know, it acts in the equation just like G acts in the FGR equation. Okay, what it is a number. You don't have to memorize it, but you have to be familiar with it. It's a number that's approximately 8.99 times 10 to the positive 9th. So let's start with that. It's a huge number. The other one, remember, if you turn back, was like 6.67 times 10 to the negative 11th. Right? So all of the things being equal, this force that we're talking about now, this force of how electrons and protons, or electrons and electrons, or protons and protons pull or push on one another, if all of the things are equal, this thing is much more strong than the gravitational force. And what are the units of this? Well, the units of this are newtons times meters squared all over, well, not kilograms squared, because the thing in the numerator of this fraction is not a mass, like this is now Q1 and Q2, whose units we have to cancel out. Q1 and Q2 are not masses anymore. This is not about obvious macroscopic massive thingy things like that. This is about charges now. Charges are measured in a unit called a Coulomb, capital C. I have to pause and talk about that for a minute. Maybe you remember it from chemistry, but what is C? C stands for Coulomb, C-O-U-L-O-M-B. Again, the guy's name, Coulomb. Coulomb is the unit, is the SI unit, for electric charge. Now, let me put that in perspective. How many? Okay, we've got like 17 minutes. Let me put in perspective what I'm talking about here. Like, we're now talking about charges. I don't know exactly what charge is. Charge is an innate or universal property manifested by or characterized by certain types of matter. Just like mass is a property manifested by matter. I don't exactly know why some matter has charge and some matter doesn't, just like I don't exactly know why matter has mass. I mean, it's just a defining feature of the stuff that the universe is made of. I'm not trying to blow it off. Like, you could spend your whole life thinking about it, and it's very interesting, but I don't really have an answer for you. It's just the building, like just like a building block of matter is pieces of stuff called pieces of mass. A building feature of matter, of some types of matter, seem to be called charge. What I can tell you about charge is where we find it and in what type size packets we find it. And of course, you've been dealing with it for years in chemistry. I know that too. Hold on, there's something in the charge. Something in the charge, something in the chat. Wait, wait. It's okay. It doesn't matter. Get it. Oh, okay. Doesn't matter. Okay. Oh, that's cool. I do get it. I think I get it. Okay. Yeah. Charge is kind of like something that matters that isn't matter. I mean, but it's a little confusing because charge generally tends to a cup. We don't find, it's hard to find charge without finding matter, but we can find matter with it. Anyway, how do we find charge? What we know about charge is what you know from chemistry. Let me get this straight right now. Like, the fundamental units of charge, like the smallest pieces that we tend to find charge in so far in nature, fundamental packets, I'll say, of charge. And I'll even say whatever, you could say the elemental packets of charge are the proton, right? One proton has a small amount of positive charge and it's about the smallest amount of positive charge we ever tend to find in nature. And it is a certain amount that I'm going to write down in a second. And so if you have 2 protons and you have 2 times that amount, right? Now the amount, I wish were 1 Coulomb. That would make all of this make perfect sense, but it isn't, because of just the order in which we discovered things and named things in the order. And we discovered things on a big scale, and then we went back and we physicists of the 19th and 18th and 17th centuries, like, it's easier to discover and work with big things, and then they figured out what was going on the small level, but they already had units that corresponded to the big level. So 1 proton has a charge of approximately 1.60 times 10 to the negative 19th coulombs. Okay, so now that I wish the number were 1, but it's not. And you don't have to memorize this number either, but it is a universal number that you could always look up because it's always the same. I just want you to get perspective that the amount of charge in a proton is essentially, I always get this wrong, wait, billion, trillion, quadrillion, quintillion, right? It's like 16, the amount of charge of a proton measured in coulombs is so small. Like the charge of a proton in coulombs, is 1.60 times 10 to the negative 19th coulombs. So that's so small. What we're in effect saying is it takes approximately 16 quintillion protons to constitute whatever 1 Coulomb of charge. Another way of putting this is a Coulomb of charge, even though that's our fundamental SI unit of charge, is actually a lot of charge. It's like 16 quintillion protons. I mean, protons are very small also, so it kind of all makes sense in the end. But if I ever say Coulomb of charge, as I'm going to say in these equations, what you should picture, if I ever say a Coulomb of charge, what I in effect mean is approximately 16 quintillion protons, i.e. the thing you find in the nucleus of a hydrogen atom, like these really small things. Picture like 16 quintillion of them jammed together in a tiny, tiny Euclidean space. That would be a 1 Coulomb positive point charge, would be like, picture like 16 quintillion shimmering protons all jammed together now in a small space. Now, is that realistic? Yeah, it's very realistic. We often have coulombs of charge. Is it something you can picture? Yes, in the same way that you can picture a bunch of kilograms located in a very, very small space. But is it a little bit harder to picture charges than it is to picture masses? Yes. That's why everything we're going to say from now on about electricity, we started today. The reason we spent 2 hours today talking about gravitation is because, as abstract as gravitation can be, at least it's about masses, which we can all sort of picture, right? So gravity is the phenomenon that governs among the macroscopic stuff that we can sort of relate to and picture in the real world that we live in, the macroscopic world that we live in. I'm here to tell you, especially if I get cut off in 9 minutes, in fact, 11 minutes, I'm here to tell you that everything we ever say about how the way protons and electrons interact or charges interact, it's all the same ideas as how planets and stars interact, at least in this context. It's all the same math and same ideas. It's just that we all know, all of us, not just students, everybody finds it a little bit easier to relate to masses than to relate to these sort of tiny, tiny, sort of invisible, sort of like two color properties called charge. So whenever you're in doubt and having a hard time picturing something in electricity, first of all, remember, you're not alone. All of us have a slightly hard time picturing something in electricity. But second of all, try to relate it back to gravity. Also note, I'm going to go on in a second, but also note, it's not a coincidence that you dove in and started playing with wires and batteries and resistors and stuff in the lab before we even said anything about protons and electrons, of which they are composed. The reason you dive in and play with wires before I even say anything about electrons or something is because that's how it unfolded in history. That's how we learned about protons and electrons in real life. Real people did, because you can't really play with protons and electrons in your hand or on the table. You can see their effects as you send them through long journeys through these long wires and turn on light bulbs and stuff like that. So how you're seeing it in the lab, and then we're sort of backing up and trying to like deconstruct the theory here in lecture. That's totally how it was all figured out in the first place. It's the only way you would have no frame of reference if you didn't. I mean, nobody, anybody, students, teachers, discoverers, none of us would have any frame of reference for electrostatic interactions unless we had both planets and stars and gravity to think about, and wires and batteries and light bulbs to get things in action to see. Okay, so you, whatever. So I'm back to the material here. So one proton has a charge of 1.60 times 10 to the negative 19th coulombs. That's like the smallest packet of charge you can ever imagine. If I talk about a coulomb, I'm talking about like 16 quintillions of those protons. Luckily, one electron, which you really are the thing that you're playing with in the lab, electron is the negative packet of charge, as you know. And it just happens, thank goodness, that even though an electron is a lot less mass than a proton, an electron is a lot also less volume than a proton. I mean, electrons are smaller thingy things than protons, but they are thingy things, just like protons are. They're just really, really small. They might be different masses and different volumes, but they have, luckily, the same magnitude of charge, just in two opposite directions. So this is getting confusing. Hold on. Okay. The charge of an electron is approximately negative 1.60 times 10 to the negative 19th coulombs. Okay, so from now on, again, this is all a little bit backwards, but I'm saying from now on, we have this force called the electrostatic force of attraction or repulsion between, and it's a force vector, just like the gravitational force vector. It's between any two point charges. A point charge would be a point charge from here on in would be a small, well, let me see. A positive point charge would be a small number of protons condensed into a very, very tiny Euclidean volume, infinitesimal volume. And a negative point charge would be a number of electrons condensed into a very small volume. Again, they could be of different magnitudes because it might be it might be 100 protons, or it might be 3,000 electrons, just like you could have a 1 kilogram point mass, or you could have a 17 kilogram point mass, right? Point charges can have different magnitudes depending on how many protons or electrons are in it, but that's what we're picturing. When we picture point charges, we're picturing little tiny bundles of protons or electrons. The force that would be exerted by one bundle of protons over here, separated by a distance r from another bundle of protons or electrons over there, would be given by this equation, which I've already written down once. It's the exact same format as the gravitational equation, right? You see that, I hope. It's, again, a scalar times a vector. The vector is the unit vector that points from one charge to the other, just like before. But now here it can be plus or minus, because Q1 and Q2 can each be plus or minus, right? Because they could be, unlike with the other thing, masses are always positive. Point masses are always positive in magnitude. So you multiply two masses together, you get a positive number, and then that negative sign in the other equation tells you, flip the vector, it's going to be a pull. Here, you multiply the Q's by each other, depending on what answer you get, that will tell you whether this R vector gets flipped or not, whether you're ultimately getting a force vector that is attractive or repulsive. Hopefully you see that. And I know we have 6 minutes left. So all of this, if you follow the math of the other, then the math works the same here. Again, it's an inverse R squared force. An inverse R squared force, right? And I'm not, and also just to say that that homework that is now not due tomorrow afternoon, but due the next afternoon, if you whether you think I've said a lot of what I've said You can do it now, is what I'm trying to say. I'm going to keep talking. I haven't like directly addressed anything in the homework yet, but when you pull it out tonight or tomorrow morning or whatever, you'll see that it's all very much on the subject of this. I think you won't find it, certainly the beginning of it, I don't think you'll find it too crazy or taxing. In fact, I'll also just quickly warn you, you sort of do one exercise in the homework that's sort of just a plug and chug. It's not meant to be a trick. It kind of is just a plug through the equation and practice and get an answer. And then you'll notice that you do like 5 more exercises that are like exactly the same thing. And you'll find it repetitive and redundant. And you're right. And it's not meant to be a trick, but it's also, and it is meant to be practiced with this one equation, but also just to warn you right now, when you're going through, if you find it redundant or repetitive, it's also not just, it's not meant just to be dreary. Like, don't stop and say, I get the point, and then just stop. Because what it's really trying to do is while you're going through, if you see a pattern of any kind, you'll see what I'm talking about when you get to the front of the sheet. But, and I know we have 4 minutes left, but when you're going through the homework sheet and you've done the first exercise, then when you go to do the second, I think it's on the front of the sheet, and you get to the second exercise. If anything comes to your mind, like, wait, now that I see what I did in the first exercise, I bet I could save time by, instead of redoing everything, just like changing one number or something. If you get an insight like that, go for it. That's actually part of the point of what the homework is trying to show you. If you feel like you can come up with tricks or cheats to make your life easier, do them, keep track of them. And I'll even warn you right now, if you come up with a seeming cheat or trick for exercise B, but then you get to exercise C and you're like, I'm not sure if that trick is worth it at this point. I think it'd be like, I could do it, but it would like actually not save me any time. I'm just going to do it from scratch again. Then you're not crazy. And that will happen. In fact, if none of what I'm saying penetrates, then don't worry about it. But if you sort of see a trick that sometimes works, but then sometimes doesn't, you're definitely getting the point of the whole thing. And I will show you that in class tomorrow or the next day. But anyway, that's a warning about the homework. Now we have like 3 more minutes. There's one big last thing I have to say that we'll get into everything. We'll get into all the unthingy stuff, and we'll get into a couple of questions that were in the direct chat, I believe. The one last big thing to say for 3 minutes, and it won't maybe even take me through it, is I'm looking at the time. We have 2 minutes. Okay, I want you to notice something. We've now established like equations for two forces. One came from like the middle of the early 18th century, and the next one came from the early 19th century. They both have the same mathematical form, which is inverse R squared, right? Also, both of them are forces that are known as fundamental. Now, what do I mean by fundamentals? I mean something very specific. I don't just mean that they're really important. I mean, they are really important, but the normal force and the friction force are very important as well. They're not known as fundamental. The tension force in any string is very important. It's not known as, even the Hooke's law force that we spent the entire first half of the semester on, the Hooke's law force is super important to this whole course, but it's not known as a fundamental force. These two forces, the gravitational and electrostatic, both have this format, this mathematical form, and they're both known as fundamental. With 1 minute left, what do I mean by fundamental? What I mean is, this is super important. What I mean is, I mean that both of these inverse R square forces also demonstrate a property or characteristics, I'm putting down the cannoli, known as action at a distance. This means they're fundamental They're fundamental in that for a mass, this is the last minute, only existence, I'm writing. For a mass to exert a gravitational force on another mass, all each of the masses has to do is exist. They don't have to do anything. They don't have to do any behavior. More specifically, they don't have to touch each other. Same thing with two charges. A proton pulls on any and every electron in the universe automatically from the moment it exists. It doesn't have to reach out. It doesn't have to shrink or expand. It, most importantly, does not have to make any material contact with the other charge for this force to be generated. That is unlike tension. That is unlike the normal force. That is unlike friction. That is unlike the elastic force. All forces, I know this is the last minute, I'm stopping. All forces are interactions, but between pairs of objects, these forces are interactions across empty space. They are non-contact interactions. They just happen automatically without any touching. And they both have the same math format. That is weird. And we have to go. And someone just raised their hand, but I think it means to tell me that we have to go. So we have to, I'll hang out for a second if there are any questions, but thank you very much. Oh, I can go back. Yes. But y'all can go. And I'm going to go back and do whatever y'all need me to do. But yes, but thank you. Yes. Goodbye. Goodbye. I'll see you tomorrow. Thank you for being so patient with everything. Yes. Have a nice day. Thank you all. Okay. I'm changing the view and I'll turn off the recording. Thank you. I'm hanging out until anybody questions, whatever, but I'm changing the recording. Thank you all very much. Thank you. Great job today, by the way. Direct chat person who just said that. Thank you. Well, thank you all. Great job, all. But yes. Okay, great. I should turn off the recorder. Thank you. Thank you. And I can turn pages for anybody who, thank you. Great job to you who just wrote that, even though you're what I'm saying. Okay. Wait, I'm going to turn on. Thank you. Thank you. Awesome. I'm going to turn off the recording. And should I go back to the other page? I don't know. Is that?